Well, welcome back to week 2. You made it so far. Today it's Kim Wilkins and
Luther Tykonovich.
We're here to talk to you about some teaching strategies, computer science teaching strategies. So first, again, we want to thank everybody who's been involved and helped make this happen. Mission, we talked about that last week. Teaching strategies. So again, I always start with the students. I'm very much into student-driven learning, and I created this after doing computer science education for 6 years. I created this document called Anatomy of a CS Integration Project, which is a doc that you have access to, but here are some of the highlights from it. And Luther, please chime in. Oh, why don't you introduce yourself first, just in case folks haven't met you yet.
Oh, right. Yeah, I teach computer science at the University of Virginia with a focus on pedagogy and diversity issues. So you'll hear a lot from me next week, but I'll also weigh in this week.
Cool. Yes, thank you so much for joining us. All right, so one thing is the projects, we like them to be authentic and relevant. You know, kids love working on real problems and solving real problems, especially problems that they themselves notice. So we want the problem to drive the project, not the CS standards. So I always go, especially when I'm working with teachers and I want to integrate a project into their classroom, I first ask them, what is it you want to get out of this project? What are the subject things that you need to happen? And then build it around that, and then bring the standards in afterwards, as opposed to start with the standards and try to wrap a project around it.
And here I believe we mean by problem, we mean the thing that the CS will solve.
Yes,
right?
Correct.
And the challenge the students might be facing or so on. And this probably applies with authentic and relevant too. There's lots of things students care about, but if you just ask them from the beginning, what do you care about? You're unlikely to get something with a little bit of guidance as to what sorts of things they should be considering.
Yes. Yeah, and I bring design thinking into it a lot to help guide that thought process for them. Another thing I often do is student differentiation through challenges. So when I go into classrooms, the computer science knowledge could be widely different. I know what my students have been like. If they've been in kindergarten and then now in first grade, I know what they did, but then there's students that do stuff on their own. And so I don't just want them to be like, okay, I'm done and finished. So I often, when I create projects, I will have sort of the baseline expectations and then challenges for those who'd like to, try some new stuff. This is really important for me, especially because, I am very good at getting students started with computer science concepts, but especially as they get into the middle school level, they're going to start getting beyond my skill level. And so it's just super important for me to recognize students as peer mentors and for students to recognize themselves as peer mentors.
I'll add to this. I teach computing professionally. It's very rare for a student to get beyond my ability, but it is very common when I have students working on different projects for there to be so many things going on that I can't handle it all myself, right? So these peer mentors are good for the students to feel like they can grow and mature into that role, but also useful at any level of your own ability and sort of managing what's going
on. One thing I think, often computer science is thought to be this really hard, tricky thing that's, something that only certain people do, but really the fundamental concepts of computer science are just everywhere around us. And so I want to help students recognize that. And this is a huge one for me. We talk a lot about failure and mistakes and getting kids and teachers comfortable with the idea that the first time they try something, the first time they code something, the first time they write an algorithm, whatever it is, it's not going to work. And that's going to happen every single time they try something new. And that's because, it's sort of embedded in you, your video, Luther, from the first week sort of really explained this well.
Yeah, I'll also add to that, in CS, you're teaching not just knowledge, but also skill. And all skills, if you think about athletics for a classic example, or art or the like, right? When you're teaching a skill, it doesn't matter how well it's explained in advance, you're going to do something wrong until you've practiced many times. And so the challenge, part of the challenge of teaching any skill is to help the students accept those intermediate failures as not indicative of their end state.
Right. So I also am very big on student choice. and creativity within design constraints. So, as you're building a lesson or activity or project, you want to have those sort of garden walls, I guess, or, some sort of constraints in which the project can be created, but then give the students as much freedom within those constraints as possible.
And what exactly that will look like will vary by student. Hopefully you'll know your students as the term progresses and understand better what they can be done. But always giving them a little more freedom than you thought will get them more engaged. And as they're more engaged, they'll apply more attention to what's going on and learn more, even if it wasn't exactly what you thought everybody should be learning at that moment.
Yeah, that's important. Also, you're giving a lot of control over the students. And so every time I do this, the students, will create something that I didn't expect. And that can be awesome, and it can also be scary.
And sometimes those scary things can be an opportunity for another lesson, right? When somebody does something that was out of bounds of what you hoped, there's an opportunity then to talk about why and have those other teaching moments as well.
And then another thing I love about computer science is they really demonstrate their knowledge through their work. The program works, it doesn't work. There's very few things, I don't know, you might disagree with this, Luther, but I think there's very few things that you can do a sort of standardized test with computer science about.
Certainly at the lower grade levels. Eventually there's computer science theory, but you're not going to deal with that. Yeah, there's this great deal of they can show you what they've done. Now this is something to understand if we go back to this idea of context. The students that can go home and play around with some of these tools on their own are going to develop more impressive work. And so there's importance to be sort of sensitive to that aspect as well. So although they demonstrate their knowledge through their work, that knowledge isn't necessarily all gained in the classroom, and sort of being sensitive to that and how the students compare themselves to each other and how you compare them to your expectations can be important as well.
Yeah, I'm glad you brought that up, because it is very important, especially for students who are new to computer science or, think that shouldn't be part of computer science. And then there's those students who've just been, doing it since who knows when. And yeah, you can't compare, you can't compare them. I tell every student, you start when you start, and you'll level up in time. You'll catch up with the ones who are ahead right now, but there's no need to compare right now. All right, so there are some specific CS teaching strategies that we're going to take you through, and instead of just listing them all right now, I will take you through them one by one. I'm going to let you take this.
Sure. So in programming, the most common term to refer to the program, the expression the human gives the computer, telling the computer what to do, we call that code. Because it looks like a code. It looks like a coded message. It's in a different language. And code is useful because both humans and computers can learn to understand it. But there's this other idea of pseudocode. Pseudocode is designed to be written in a language you're familiar with. For you and your students, this is probably going to be English. But to have some of the structure that a computer needs to understand what's going on. And so instead of just being a verbal description of the goal that we want to do, it will be a sort of a line by line, one step at a time, what should happen. And this can be a very useful intermediate state to go from saying that we need to have a game of asteroids to saying we need to have a sprite and a spaceship. And when they touch each other, this thing should happen, right? Putting it down in those smaller steps and writing it down in English in this pseudocode form can be very useful in helping to understand what it is you're trying to do, to formalize your approach. It can also be helpful in the other direction. When students have some code they've written that isn't behaving the way they expected, it can be very useful to say, okay, how would I turn this code into pseudocode? Can I turn each individual piece of it back into English describing what it's doing as a way of trying to understand the difference between what we meant to say and what we actually said? Because computers, well, very fast, are very bad at understanding our intent.
Yeah, they're very literal. One of the things I like to do with this kind of activity, especially with younger kids, is either have them think about a daily activity, what are the steps it takes them to get to school, and then sort of write those out as a pseudocode. Or I'll bring in a recipe, that's written in sort of traditional recipe style, and then turn that into pseudocode.
It can also be useful to have them follow these instructions. So in my
Right.
introduction to programming classes in college, I will often have an exercise where they're writing out instructions in pseudocode about things humans could do, and then trading it with somebody else. And then the other person is instructed to follow the instructions literally, but not the way they were intended, to sort of see the scope of how difficult it is to express things clearly. Whether that's exactly appropriate for your students may vary, but getting them used to this idea that there's a set of steps, we follow them one at a time, will get them used to the way the computer is thinking about the task.
Yeah, there's an unplugged activity that was linked in week 1. That's, I think, My Robotic Friend, that does just that.
Okay, so use, modify, create is a teaching strategy that can apply in a lot of places, but is very common in computing. The basic idea here is that you first give the students some artifact to use, a piece of pseudocode to follow, a piece of code to run. And you have them just use it and see what it allows and doesn't allow. And you give them a specific set of things to modify. Change it so that it repeats 5 times instead of 3. These kinds of very specific small changes. Depending on the size of the thing, you may give them several of these of increasing complexity, so that they understand through this modification how each piece contributes to the whole. And then they're ready to create something of their own using similar tools.
I'm a huge fan of this strategy. In fact, this is the way I learn computer science and different coding languages, is I'll just go and find something that already exists, remix it, and just experiment with the things I can change. Are there variables I can change? Are there colors I can change? Are there sprites I can change? I think it's just an awesome way to learn what's happening, and a great way to experiment with making mistakes, because it's very low cost. You can always change it back.
Right. This also is, if we think about programming as a language, as that's the terminology we use internally, this is sort of the closest we usually get to reading, as opposed to only writing or listening instead of only speaking. This is the chance to say, here is somebody else's expression in this code, and understand what it means, so that you can develop that sort of fluency and that sense of literature of the different sorts of things people can do with it.
And the Scratch platform is really based on this model, and you'll find when you get into the Go OpenVA, it's also based on this model. So pair programming is one of the activities I love. It's super helpful, especially if you don't have a lot of devices. So I use it with robots, computers, tablets, whatever the device is that, the Makey Makeys, whatever it is. And you identify a driver and a navigator. And the driver is the one who's actually hands-on with the device, so the tech. And the navigator is the one who is offering advice and doing some debugging work, but they're not hands-on. And the idea behind this is at timed intervals, and I usually use 5 minutes with K through 8, you have them switch so that then the navigator becomes a driver, driver becomes a navigator. And the important thing is that you want to make sure that everybody gets hands-on with the tech, and everybody is comfortable with it and gets to try things out. And you're going to have some of the kids who would prefer just to hang out and be the navigator, and you're going to have others that would prefer to hang out and be the driver. But we really want to make sure that everybody starts getting comfortable with each of those roles.
Yeah. When you're doing pair programming, you'll find that a lot of your attention as a teacher will move from explaining concepts and helping students to guiding the process they're engaged in, making sure they're talking to each other respectfully, making sure the driver is driving and the navigator is navigating, making sure they do change roles. But there's significant research that suggests this leads to significant learning benefits. As they take turns essentially explaining to one another, this helps reinforce their understanding and helps them learn more. So while it can be useful if you have limited devices, I also use it in college where everybody has their own laptop. I make half of them shut their laptops and pair up, because the learning that comes out of this is great, but it does require some supervision to make sure they engage in it properly.
Yep. So I had not heard of this one before.
Yeah, so buddy programming is a newer terminology. There was sort of an observation that because pair programming requires supervision to work out properly, In some cases, you don't have the resources or attention necessary to sort of keep it going. And so buddy programming is a less formal way of pairing. Instead of having two people working on the same thing together, they're working side by side to create a similar artifact with their own device. It's a lot easier to run. Students will adopt to it pretty naturally with very little guidance. You just say, talk to each other, work together to build something is usually the whole guidance you need to give. Occasionally you do a little bit of, listen to both people's opinions kind of thing. It doesn't have quite as good results in the research as pair programming, but it's still significantly better than solo work and can create a sense of community, particularly if there's a challenging task that requires a fair amount of thought to get done.
And this is pretty much like the real world. Like when you're programming in the real world, you're not sitting and doing everything on your own. You're working with others to get that code working.
Yeah, only very small programs are done by yourself. You're always working with somebody else in some context.
Debugging. Oh yes, this is I love talking about debugging, and there is this, I think it's a myth, but that the idea of bugs came from when Grace Hopper was working in computing, and that's when there was giant machines that took over whole rooms, and her code wasn't working, and she didn't think it was her code, and then she went and looked behind the wires, and there was a literal bug shorting out a wire. So not sure if it's true, but it's attributed to that. And I love Grace Hopper, so I love the story.
The idea of debugging, the analogy here is the same as the analogy of trying to find where has a bug gotten into a room-sized computer, right? Something didn't work the way you hoped it would work. What didn't work the way you hoped it would? How did that happen? And so the challenge here is to describe what went wrong and to find where it is that something happened to make it go wrong. As programs get larger, this becomes more complicated, but even for very simple programs that just have a couple of actions, it's still easy to get a little piece of it wrong, and sometimes that will result in unexpected behavior.
And one of the things we didn't put as a bullet, but that I often do with kids when they're learning about debugging and learning to debug, is to think about how the steps that they'd go about to actually fix the problem. So, there can be a tendency to be like, oh, I'm just going to change all these things and then see if it works. Well, if you do that, if you're not very methodical about changing one thing at a time, you could add to your problems.
Mm-hmm. Right, changing one thing at a time and changing it back if it didn't help. Right. It's also worth remembering that humans are smarter than computers. And so there's this idea, we have a bullet point about tracing the code. By tracing code is this process of having humans walk through the code and see what every step does. It requires a little discipline not to skip steps, to do exactly what it says every step along the way. But as you'll go through that process, you'll realize, oh, it should have done this and it did that instead. This process of tracing can be modeled by having the whole class participate, having them take on the role of different parts of the program, such as variables. And then as they get experience with that, they can do it on their own when they look at code. So that eventually, they can often look at a program and find the bug even without trying anything. They can just look at it and understand. That comes later, but initially getting this idea of experimenting and understanding what it can do can be very useful.
Yep. And of course, bugs are expected. Like they're going to happen, and that's great. And so, hunting them down is sometimes a fun job.
Code reviews are a practice that's come out of professional software engineering, people that program for their living do this often. And the basic idea is after you create the program, you try it out, you think you understand what it's doing, you then still bring in other people to discuss the program together. And this can help you understand what's happening, and help you notice places where it might do things wrong and so forth. So this remains a practice that's useful at all levels of ability. When people are first learning, it can be useful to ask simple questions that try to measure, do they understand what happened, or have they not yet understood? A lot of these are sort of related to back in the modify step of use, modify, create. Okay? We're looking at the code and we're asking questions to help students think about what would happen if I changed this part. We're back to pseudocode. How would I have described this in English? Sometimes we can also think about the fact that almost every action can be described in many different ways. You can say, is there another way to write this? To help students understand that their code doesn't need to look like somebody else's to also be correct. Or could we make this shorter? is a challenge question that can help people think about the expressivity of their language, or comparing different programs and seeing how they're the same and different. You don't need to do all of these, and you don't necessarily need to do them very often, but occasionally pulling up some code and talking through it, having the students participate and share their ideas, can help them understand it more fully. This can also promote a sense of growth mindset, as they understand that they understand more than they used to, right? Because they started out in general not understanding how something works, but after they've played around with it, tried some different things, programmed some, they're likely to recognize that they now know a great deal more.
So this is one I like to use a lot, especially with a bigger coding project. So there's a project I do in 4th grade where they're going to code math games for 2nd graders. And so they have grand plans about what they'd like to do. I need to give them those design constraints. And in the initial year or two that I started this project, I gave those design constraints. But then as there were games to play from the previous year, we would play those, and then the 4th graders themselves came up with their design constraints and what the criteria should be for how their games came out. And I really like that. I think it, it gives them ownership, and also we can talk about expectations and things like that as well, if things are going to be a little too hard to do in the time frame, or if they're going to be too easy to do in the time frame.
I'll observe that usually people will bite off more than they should rather than less.
Yes.
When they're first starting out. They have grand dreams. I also comment that although they don't often come out in the conversation, beware of anything that looks like it should be perfect, it should have no bugs. Although that would be true if they were delivering a final software project. Even full systems usually won't do that until the 2nd or 3rd release, because we really like this sense of experimenting, trying things out, get the basics down. And there may be a few places that are a little off, that's okay. And so if those things come out, it's important to sort of encourage that they're learning and they should experiment and not worry as much about perfection.
All right, well, those were the strategies. We hope that they're helpful and that you'll be able to incorporate them into your CS lessons that you're creating or remixing. And we hope that a lot of that work is going to happen at GoOpenVA. It's an open education resource initiative from Virginia. And we've created a group, the Charlottesville Computer Science Community. Even if you're not in Charlottesville, please join, please add resources. We really want to help seed this resource with lots of computer science, especially integration resources, lessons, activities. And I'm going to be interviewing Jean Weller, who is the big proponent of GoOpenVA within the Virginia Department of Education. So there'll be a podcast that you can listen to more details about it. And I'm also going to do a little video tutorial to take you into the system. If you're in CS Institute, you've already probably seen it by linking to some of the lessons that I have up there. But it's a really great project, and I'm really excited. While CS Institute is happening, I'm actually reworking my resources because I have them scattered all over the place, and I'd like to have them nice in one nice place like this repository. So we have the same sort of weekly flow. There's going to be some videos and readings to do. There's going to be some do activities to do that relate to computer science. We will still have our virtual office hours and show and tell. We've been talking as a group, and we might turn some of those virtual office hours into discussions about certain topics. So we'll definitely let you know if that's coming. And the show and tell, all we're really hoping is that you can come and share something you've created, something you've learned, some revelation you've had, just a way to kind of get together as a community and share the learning. And of course, everything for the CCSC cohort is on Canvas, and the CS Institute is at that web address. And please feel free to send an email to spark@stav.org if you have questions.